Oh, all right, dear students. Well, let's start a new chapter. This will be on. Let me see how everything works. Yes. So now we start with linear DAEs, but now we consider no more the constant coefficient case, but now the coefficients will be on time, depending on time. So this is chapter 4. Can I have another color, please? Chapter 4. Still linear DAEs, but now with variable. People call this variable coefficients, or what we also might use instead of variable, time varying coefficients. Okay, and that will take us a number of lectures, because theory is very rich and a lot of technicalities, but still I think that's something that one can understand with basic knowledge of linear algebra. And again, there are nice examples how linear algebra and differential equations, in this case differential algebraic equations, play together. Alright, but let's start with what we mean by this particular linear DAEs with variable coefficients. This means from now on we consider E of t, x dot of t as a of t, x of t plus a right hand side, which now means that that E and A are matrix valued functions. So this means we will assume that they are continuous functions that are defined on this time interval as we had it before, and now they map into, for sake of generality, complex in the field of complex matrices, rows and columns. So that's now these E and A that define our differential algebraic equation. And we will have F. Well, we can just write it like that, and then we have to make it smoother at some point of time. So for that we can define it like that, and there might be, and possibly, so we will also talk about the initial value problem and initial value, namely we will require x of t0 as x of 0, and this is some vector in the Rn. Okay, and we will talk about solutions here, and solutions, so here this x will be the solution that we talk about, and really just the same definition applies there. Solution should be differentiable, and it should fulfill this differential algebraic equation. And if we talk about the initial value problem, then it should also be be x equal to x0 at time t0. And here, and the big difference, and this really makes a huge difference, is this dependence on time that we have here. Before that, E and A were just matrices, and now E and A they can change with respect to time. And then of course you can think, okay, let's have a look how we approach this. Back to my normal color. So for solvability, we were considering regular matrix pairs maybe you recall these theorems that we had. There exists a solution, there exists a unique solution if and only if there is E and A form a regular matrix pair. And let me just recall this here briefly. We had E a regular if and only if, so in the sense of a definition, this was defined to be like that the determinant of lambda E minus A is not completely zero all time. So there's a lambda, so that this is invertible. No one may think of extending this regularity to time-dependent case, and then a very strong notion would be that one wants to have this regular independent what the time is. So what about considering to have the determinant of lambda E of t minus A of t. So taking the determinant of that, and this is now a polynomial, of course, in lambda, but it also depends on t. So for every t, this will be again a polynomial in lambda, and then it might, well, it sounds very sensible to require that this is not zero so this is not completely zero all time for all lambda, but no matter what the t was. So for all t in this interval. So this seems like a very strong assumption, and also, well, it fits very well into here. If E and A do not depend on time, then this is certainly the same here, and then one requires this for all time, and this seems like a very strong notion. But see the following examples. It will turn out that this regularity, even if it does not depend on time, if it's uniform with respect to time, this does not tell as much about whether the solution is there and whether it is unique. Okay, see the following examples. So let's start with example. What number was it in the script? Example 4.1. Here the DAE was here's my color. So we consider this DAE t minus t squared minus 1 t here dot x1 of t x2 of t is equal to a of t minus 1 0 0. That's basically a of t minus 1 0 0 x1 of t x2 of t. So we consider this DAE. Here we have this matrix E of t, this is this matrix A of t. And well, one can, of course, what is determinant of E of t minus A of t? That's, well, for 2 by 2 matrices there is a formula for the determinants. One can just calculate that. I just, well, okay, one just to see something familiar. So this will be minus lambda t squared. So minus lambda t minus a of t, so this will be plus 1. Here we will have lambda t squared here we will have minus lambda, and here we have lambda t plus 1. So we need to compute the determinant of that, and this is like main diagonal minus anti-diagonal. So this will be, I write it there. Okay. 1 minus lambda t, so times 1 plus lambda t. I switch these entries. Minus what is here, this becomes a plus, because here's a minus, minus plus lambda square t squared. This is 1 minus lambda squared. So this is exactly 1, independent, no lambda, no t, this is just 1. So this is certainly very regular, depending on whatever t is there. So one may assume, so if we could transfer this notion, then this should somehow imply that there is a unique solution. But so regular independent of t. Still, there is this following problem. Take any c to be a differentiable function. So in C1, let's see. In this case, there is a 2. No. This is just a coefficient function, so this should be a differentiable function with values in the complex numbers, with c of t0 is 0. Need an example. What about take t0? No. Example, sinus of t minus t0. This is 0 at t0, and this is differentiable. And then the function x that takes t and maps onto c of t times t and 1 actually solves this e of t x dot of t as a of t x of t, as we have with this e and this a. One can try to confine this, but this is straightforward, and this means this solves this with x of t0 is 0. So we have constructed a solution to the homogeneous problem. Since there are very many such, so already we can just multiply with any number. So say then alpha times this will also be a solution, because this will be 0 here and it's differentiable. Well, you can think of many functions C that have this property. So this means infinitely many solutions to the homogeneous problem. Homogeneous problem. and this basically means no uniqueness. Okay, so this is an example where this pair of matrix functions seems perfectly regular, but well, there are infinitely many solutions to that. And even worse, next we will have an example where the matrix function seems to be singular in a very bad sense, so that it's nowhere regular. And still we will see there is a unique solution to that. So this is example 4.2. And here the DAE goes like, so this is again the E matrix, 0, 1, minus t, x dot x2 as time t minus 1 and t 0, 0, x1, x2, t, and now we have a right hand side here because and we have splitters as well. Consider, so again this here is e of t, this here is a of t, and then again we can consider the determinant lambda e of t minus a of t, and since one can already observe that whatever the t is, this line is just a multiple of this line, and so this will be just 0 all the time because these lines are the lines are linear independent, so yeah, whatever the alpha is, whatever the t is, the lines are linearly dependent, so it won't have full rank, and that's why there will be a 0, the determinant will be 0 for all t, and this looks like not regular in the sense that we were mentioning before. However, left, looking here at the first line, so the first line says that 0. Here, the first line is just 0 on this side, and here we have minus x1 of t as plus t of x2 of t plus f1 of t. So this is this. Or we can just put this to the other side. x1 of t as t x2 of t plus f1 of t. And this in particular means, so we just derive once with respect to time. We get x1 dot of t as, here we need to use the product rule. This will be x2 of t plus t x2 dot of t plus f1 dot of t. Okay, and that we can rearrange to, no. And what we then do is taking this part and putting it here as well. So from here we come to x1 dot of t minus t x2 dot of t is the same as what is left here, x2 of t plus f1 dot of t. And now that's exactly what is here in the second line. here the second line says x1 dot of t minus t x2 of t is just f2 of t. So we can replace this here by this other equation to be just f2 of t is x2 of t plus 1 dot of t. Well, this basically means x2 is f2 of t minus f1 dot of t. And then, where do we have it? Was there? Yeah. And this, okay, don't be lazy. Sorry, this will be the third equation that we use. Oh. The third relation from here, since this here is already x1 explicit, we put this in here, and then we get x1 is t times x2. x2 we have here, so t times f2 minus f1 dot, and f1 plus f1. Well, and that's now a very explicit form of the solution in terms of the right hand side. And when you have this explicitly, then it's unique. So you have a right hand side, x1 and f1 and f2, and that defines your x1 and x2. So no other chance for another solution. So what we take from here, not regular but unique solution. Unique solution to e of t x dot of t is a of t x of t plus f of t. And what about the initial value problem? Yeah, you can use the same arguments. Then you just choose the initial value to be x2 at this time and x1 at this time, and that's also given. So no, the initial value will not change anything to that. And the same. Oh no, that was 0. So this is okay. All right. And what does this now mean for us? So conclusion here. We need more concepts. So it's not sufficient to take the constant coefficient case and add the t to that, and then consider everything depending on t. But there needs to be more to that. And we will do this in the next lectures. Today there's left to introduce 2 more definitions of equivalence. And let me show you once more how this equivalence was used in the constant coefficient case, and then it becomes a bit better understandable why this looks like that in the case of variable coefficients. So we had e x dot as ax. This is the constant coefficient case. Ax dot is ax plus f of t. And we could transform this into e tilde x tilde dot as ax tilde a tilde plus f tilde of t, with pq invertible, ea tilde is peq paq. This here is important. X tilde is wrong. And x is given as q x tilde. That's how they relate. And this in particular, so this will be important, this in particular means that x dot is just q times x tilde. This is x tilde dot. So this gives the relation of the time derivative, so constant coefficient case. Now here the variable coefficient case. If we want to et x of t, a of t, x of t plus f of t, and now we want to use p and q, time varying and pointwise invertible. So yeah, this pointwise invertible means that for every t, pointwise invertible means p of t, q of t invertible. This makes a lot of sense. So we can't do without that, because if they're like not invertible is the zero matrix, and if we set something to zero here, we cannot recover this anymore. So pointwise invertible is important. Now p and q will depend on time. So multiplying by p of t, no difference. I mean, we can just multiply here with p of t, p of t, p of t, doesn't change, and then immediately gives, for example, f tilde of t to be p of t, f of t. More about state transformations, state transform. One certainly wants to do it just like that, so x should be q times x tilde. X of t should be q times x tilde of t. Well, because this is how it works. So we have e of t as a of t plus f of t. That's the actual equation. F of t. We wanted to put, so that's the equation that we have. X dot of t is x of t. And now we want to replace this here, x of t by q tilde xt. So how do we do this? So here there was this x dot of t, and this now is q x tilde at time t, but time derivative of all that. And here we can just q x tilde of t. Okay, this is replacing x by q tilde, x of t by q x tilde. And same way we have to replace x dot of t by q x tilde dot. That's what is here. Okay, and then this here simply gives a of t x a of t q of t. Let's keep this together as this one new matrix. x tilde of t. So this is more or less the new coefficient here. But here we have a e of t derivative here, because this is now a product of time-dependent functions. So this will be q dot of t x of t plus, that's not nice. Okay. E of t, and here we have q dot of t x tilde of t plus q of t x tilde dot of t. Yes. And what we see here, so this is here we see the x tilde dot. It's the x tilde dot, and here there is an x tilde without the dot, so this should certainly go over here, because here we have the coefficients that come with the x tilde. Got this. Okay, and that's what we do. So what we will get out of here is e of t, q of t, x tilde dot of t. And here we have a of t, q of t, as we had it before. But now this term here, e of t, q dot of t, will be added. E of t, q dot of t, x tilde of t, plus f of t. And now really we can just multiply with a p of t. So this will give us p of t, p of t. Okay, p of t to be, this is e tilde of t, and all this here is a tilde of t. And well, and that's how global equivalence is defined. And in the script, that's definition 4.1. For that one needs p to be as a continuous function. What's that? Okay, p to be p to be a continuous function from this interval to m times n complex matrices, piecewise invertible, pointwise invertible, p of t invertible, q to be in C1, so here we need this derivative of the q. Same here, q of t invertible. Well, q dot can be singular, and e tilde a tilde is PEQ and PAQ minus PEQ dot. That's the definition. And the lemma then says that this is an equivalence. This is an equivalence relation. So here we use also the tilde. EA is equivalent to this matrix, pair of matrix functions is equivalent to this pair of matrix functions. Well, if there is this Q and this P, such that this relation holds. Oh no, sorry. Computer, no. I'm losing my computer. Oh. Okay, so here's equivalence, and then one writes as we did. So we use this tilde to denote this equivalence. And then I want to shortly go into this local equivalence. This is motivated by global means that EA is equivalent to EA tilde globally if, well, for example, if E of t is Q of E of t is P of t, E of t Q of t for all time. So this definition is local equivalence. If like this equality holds for some time, for some times t. For example, then say A of ti is P of ti, A of ti Q of ti minus P of t. So say for sometimes ti, Q E of ti, Q dot of ti. Well, and since if it's only for sometimes, there's no more functional so the Q dot and Q. So on discrete times, it does not make sense to talk of Q dot to be the time derivative of the Q. So one can just replace these with say Pi, Qi, and here this can be just the Ri. So this is now not the poor definition that you find in the script, but this is why this is the local equivalence. So the definition basically says EA is equivalent to E tilde A tilde if there exists P, Q, R. P and Q should be invertible, R not necessarily, so that EA is P, E, Q, P, P, no, computer please, okay, P, A, Q minus P, E, R. Okay, so these are these basic notations that we will need.